Hi guys, it's me again. So today, rather than start with a do now, we're going to start with a think now. What do you think would taste sweeter? A cup of tea with 1 sugar packet in it, or a cup of tea with 10 sugar packets in it? Well, you hold on to that thought. Because which cup of tea has a higher concentration of sugar? The cup of tea with 1 sugar packet, or the cup of tea with 10 sugar packets? Now my guess is you know the answer to this, right? You know that it's certainly going to be sweeter if you have 10 sugar packets in your cup. And if you have more sugar in the tea, the concentration of sugar is also going to be higher. So do you think your answer to the first question kind of helped you come up with an answer to the second question? I think they kind of logically follow. The more sugar, the sweeter it is. The sweeter it is, the greater the concentration of sugar. So today, we're going to start talking about concentration. And no, I don't just mean thinking really hard. I mean concentration, or how much of something you have, right? Specifically, how much of a solute you have in a solution. So today, by the end of this lesson, you're going to be able to describe and calculate the concentration of a solute in a solution, what we're going to now refer to as molarity, using table T. So you don't have to memorize any formulas, you just have to bust out your reference tables. Okay? Now, last time, or for the last PowerPoint, I asked you, what do you think would make a solute dissolve faster? And we talked about stirring, we talked about crushing up the solute till it's really in teeny weeny pieces, and we also talked about raising the temperature, right? Adding heat. So all of those things will help your solute to dissolve faster. And kind of keep this on the back burner, right, in the Rolodex of information, because this is going to come up again in a few weeks or so. So, right, adding heat, stirring, and crushing up the solute will all help it to dissolve faster. All right, so let's keep going. Now, if you've ever had a nice, refreshing glass of soda, maybe you prefer seltzer on a hot day, you know that as you take that first sip, you can feel all those little bitty bubbles hitting your tongue and your mouth, and maybe even some up your nose. That kind of hurts, but whatever. Well, gases can be solutes. Gases can dissolve in liquids too. Who knew? As a matter of fact, it's carbon dioxide gas that makes drinks fizzy. So whether it's soda or seltzer or anything that they call sparkling, right? Like champagne or sparkling wine, it's gas. It's carbon dioxide gas that has been dissolved in the beverage that's responsible for the fizz. Now, gases are awfully unique because we just said how if you raise the temperature, if you add heat, it'll make the solute dissolve more easily. But gases, it's just the opposite, actually. Gases become more soluble as the temperature decreases. So the colder it gets, the more soluble the gas becomes, the more easily the gas will dissolve in the liquid when the liquid's nice and cold. Okay? So which soda do you think would go flat or lose its fizz first? Think about what I just said. Colder temperatures make the gas dissolve and stay in the liquid. So who do you think would lose its fizz first? Well, I'm not going to tell you. You can click on this link in the PowerPoint, or I've actually posted the link on Google Classroom. And it's a 3-minute video. It's really kind of cool, where a teacher demonstrates what happens to the fizz when the solution is either warm or cold or room temperature. So you might have an idea of what the answer to this question is, but I promise you those 3 minutes will not be wasted. It's pretty funny. Okay? So check out this video. I'll give you the answer at the end anyway. So, I say so a lot, I'm realizing. Anyway, concentration. Here we have a picture with 5 cups of water with different amounts of red food coloring in each, right? Which end has more food coloring? If you said this end, the darker one, totally right. The more food coloring you add, the darker the liquid's going to become. So which end has less food coloring? Well, if you said that end, you're totally right. The less food coloring you put in, the lighter the water is going to appear. So, less solute way on the left, more solute way on the right. That brings up 2 very important terms when it comes to solutions. And that's diluted and concentrated. So a solution is dilute when there's not a lot of solute. So if you look at these pictures and you take a look at this guy right here, see how light in color that is? Because it is dilute. There's a lot of water, but not a lot of food coloring. Whereas if you look down the other end and you look at this one, it's really dark. Because even though you have the same amount of water, you've added more food coloring. So the more solute you have in the solution, the more concentrated it is. The less solute you have in the solution, the more dilute it is. And I bet you can think of beverages that might be more concentrated than others. The sugar example I gave you in the cup of tea. Some people like to have unsweetened iced tea. Or maybe they only put 1 packet of sugar in their iced tea. So it gives it a little sweetness, but not much. So that would be a dilute sugar solution. But if you're one of those folks who grabs like every sugar packet in that little cup and shakes it into your drink so you end up with like sweet tea, well, that solution is going to be more concentrated with sugar. All right? Kind of making sense? All right. So, molarity. No, not that kind of molarity. I'm sorry. The molarity we're going to talk about has to do with measuring concentration of a solution. So when we talk about how much is in that solution, we're talking about molarity. And we use, or I should say it's expressed as moles of solute per liter of solution. And when you take a look at table T, right, that last table on your reference table with all the different formulas, there's actually a formula to calculate molarity. The formula is molarity equals moles of solute over liters of solution. So it's moles per liter. Kind of makes sense, right? So what we're going to do for the rest of this little presentation here is we're going to practice with this formula. we are going to practice using the molarity formula. And I'm just going to turn this screen in the hopes of making it, look at that, a little bigger, so that you can see it better. Okay? So let's take a look. Oh, totally forgot that was there. Anyway, the greater the molarity, the greater the concentration. Because remember, molarity is concentration, right? It's the sciencey chemistry word for concentration. So if you increase one, the other one goes up. Same thing. Okie doke. Here's a question. What is the molarity of an aqueous salt solution, KCl, that contains 4 moles of KCl in a 2-liter solution? So, right away, they're asking about molarity. Let's do this one. They're asking, what is the molarity? So, here's the formula, right from table T. Molarity equals moles of solute divided by liters of solution. So we're just going to plug in the numbers from the question. We know that there are 4 moles, so that goes on top. And there are 2 liters of solution, so that goes on the bottom. And then do the math. 4 divided by 2 gives you 2. And we're going to use a capital M as the unit, right? And when you look at something like that, you would call that a 2 molar solution. So 2 with a capital M next to it is 2 molar. If it was a 3 with a capital M next to it, it'd be 3 molar. If it was a 1 with a capital M next to it, you got it, 1 molar. Very good. Okay, so let's try a couple together. So you can see how to apply this formula, because it's really not too tricky, I promise. So, what is the concentration of a solution containing, it's not working for me, I apologize. What's the concentration of a solution containing 15 moles of copper sulfate in a 3-liter solution? So, they're asking about concentration. So when you look at table T, there's a box that says concentration. So you're going to use one of the formulas in there. And since they're also talking about moles and liters, we know that's going to be the molarity formula. And the molarity formula is molarity equals moles of solute divided by liters of solution. So let's plug in our numbers. So what is the concentration? So that means molarity is going to be our X. Now, moles of solute, it tells you the solution contains 15 moles. So that's 15 moles on top. And then liters of solution, it says there's 3 liters. So if we do the math, 15 divided by 3, we get a 5 molar solution. So what's the concentration here? 5 molar. Okay? So with these questions, you're going to be given 2 of the 3 variables. You have to solve for what's missing. All right? Let's do another one together. What is the concentration of a solution containing 3 moles of sodium hydroxide in 3 liters of solution? So, they're asking about concentration. So I'm going to go to table T, look for the box that says concentration, right? And use one of those formulas. In this question, they mention moles and liters of solution. So I know to use the molarity formula. Molarity equals moles of solute divided by liters of solution. So capital L here is the abbreviation for liter. All right? So what is the concentration? That means molarity is going to be our X. Moles of solute, well, it tells us here there's 3 moles. And liters of solution, right? There are 3 liters. So you do the math. 3 divided by 3 gives you 1. So this is a 1 molar solution. You obviously can use your calculator. More often than not, you get the math is pretty simple. You're going to get whole numbers like 1, 2, 3, or maybe 2.5 or 3.5, usually. Okay, occasionally you get something a little weird. But using the formula is going to be exactly the same. You're going to be given 2 of the 3 variables you need to solve for the one that's missing. All right, let's do another one. What is the concentration of a solution containing 7.5 moles of hydrogen bromide in a 0.5 liter solution? Alrighty, so they're asking again, what is the concentration? So we're going to go to table T. We're going to look for the box that says concentration. And in this question, again, they mention moles and liters. So that tells me I have to use the molarity formula. Molarity equals moles of solute over liters of solution. Okay? So what is the concentration? Well, that means molarity is going to be our X. How many moles do we have? Well, here it tells us 7.5. And how many liters of solution? Well, it's right here. 0.5 liters. So when you do your math, and again, use your calculator, and you take 7.5, divide it by 0.5, you end up with a 15 molar solution. So the concentration in this situation is 15 molar. Okay? So the question asks for concentration. You go to table T. There's 1 box for concentration in table T. And there's 2 formulas in there. So you use the information they give you in the question to figure out what formula you need to use. Okay? I know you guys can handle this. No question in my mind. Alright, so let's move on. Now, sometimes the question can be asked in a slightly different way. So this one says, how many moles of hydrogen chloride, are in 4 liters of a 0.5 molar aqueous solution? So they're not asking for concentration here. They're asking for moles. So you're going to use the same formula because they're giving you the concentration and they're giving you liters, but they're asking how many moles you have. So when you plug it in, 0.5 molar is the molarity, X for your moles of solute, and then 4 for your liters. And if you think about this, it's kind of like if you put this over 1, and then you can cross multiply. And when you do that, you end up with X being 2 moles. So how many moles are there? 2 moles. Okay? So again, it's the same formula, and they're giving you 2 of the 3 variables. You just need to solve for what's missing. Okay? Again, I know you can do this. Absolutely have complete faith. So, let's try one together. How many moles of solute are contained in 0.2 liters of a 1 molar solution? So, we have concentration here. They're asking about moles, and we have liters. So I'm going to go to table T, find the box for concentration, And what formula has all three of these variables in it? You guessed it, molarity. So we're going to use the same formula. Molarity equals the moles of solute divided by the liters of solution. So let's see what they've given us. We know molarity. It's right here. So this is a 1 molar solution, right? That doesn't really look like a 1, does it? I apologize. Sorry about that. So this is a 1 molar solution. Now it says how many moles? We don't know, so that's going to be our X, is the moles of solute. And then the liter of solution, they tell us right here, is 0.2 liters. So again, all we're going to do is we are going to pretend like this is over a 1 and cross multiply. So when you do that, you end up with X equals 0.2 moles. Okay, so in this solution, you would have 0.2 moles of solute. Same formula, we just use it a little differently. Okay. One more. I promise it's the last one. How many liters can be found in a 3.2 molar solution containing 6.5 moles of solute? Whew. Okay, so what do we have in this question? We have concentration, right? That capital M tells us we have molarity. They're asking how many liters, so liters is going to be our X, and they give us the number of moles. So we're going to use the molarity formula. Molarity equals the moles of solute divided by the liters of solution. You guys miss me, I know you do. Anyway, so here we have for molarity, we have 3.2 M. Moles of solute is right here. We have 6.5 moles. And we said that the liters was going to be our X. So, this is going to take a little bit of rearranging, right? Again, you can put this over 1 and then cross multiply, and you get 3.2x equals 6.5. And then if you want to get x by itself, you can divide both sides by 3.2. This cancels out, and we end up with, if you divide 6.5 by 3.2, you get 2.03 liters. So this is your answer. Okay? So the molarity formula, you're going to find that right on table T. No need to worry. This guy is right on table T. And the question will give you two of these three variables, and you just need to solve for the one that's missing. Okay? Now the exit ticket for this, couple of those questions are calculating molarity. So if you can follow along with what we did here, you'll answer those questions. No problem at all. All right? Okay, great. So just one more thing we kind of have to talk about. It's an interesting fact that if you add solute to a solution, it causes some of the physical properties of that solution to change. As a matter of fact, when you add solute, boiling point goes up and freezing point goes down. So mixing salt into water, for example, causes the boiling point of the water to increase and the freezing point of that water to decrease. Why? Because it's a solution now. So we call that, the fancy name for that in chemistry, is boiling point elevation and freezing point depression. Okay? When the boiling point goes up and the freezing point goes down. Now, you've probably seen this in action in your own homes or just outside your home. All right? Now, a plain water in a pot has a boiling point of 100 degrees Celsius. If I add 580 grams of salt to that water, it increases the boiling point by 5 degrees, right? The boiling point's now 105. Well, if you've ever made pasta and you were told to add salt to the water, not only are you adding flavor to the pasta, but you're creating a salt solution. And it's going to cause that water to boil at a higher temperature because it has salt in it. And that may very well be why your pasta is cooking faster than it says it will on the box. Interesting. Now, can you think of a situation where you might use salt when it's cold? Right? Here we're talking about using salt when something's hot. Well, let me tell you something. The freezing point of water is 0 degrees Celsius. Now, if I add salt to that water, it changes the freezing point considerably. The freezing point goes way down. So, if you put salt on your sidewalk in the winter, right? The sidewalk gets icy and you shake salt on it. Putting salt on that icy sidewalk actually lowers the freezing point of the water, right? Because ice is water. It lowers the freezing point of the water so the ice starts to melt. Meaning the temperature outside would have to get much colder for that salt water solution you just created to freeze up. So that makes it safer to walk on your sidewalk. So little did you know that making macaroni and salting your sidewalk in the winter, well, you've been doing chemistry the whole time. Who knew? So, let me see if I can get rid of this. The more solute added, let me go this way. The more solute added, the more the boiling point and freezing point change. Meaning, the more concentrated the solution, the more you're going to see the boiling point go up and the freezing point go down, right? So if you have a 1 molar salt solution, that's going to have a higher boiling point than just plain water. But if I increase the concentration to 2 molar, it's going to cause the boiling point to go up even higher. So a solution has a higher boiling point than the boiling point of just the pure solvent. So a salt water solution has a higher boiling point than just plain old water by itself. Now conversely, a 1 molar salt solution does have a higher boiling point than plain water. Oops, I messed up. Sorry. That's supposed to say a 1 molar salt solution has a lower freezing point. I apologize. I should say lower freezing point. Sorry about that, kids. So, I did it again. So these should all say lower freezing point. I apologize. I'm going to have to change that on the PowerPoint that's online. So, a 1 molar salt solution has a lower freezing point than plain water. Now, if you up the concentration, it's going to drop the freezing point even more, right? So a 2 molar salt solution has a lower freezing point than the 1 molar solution. I apologize for that. In simple terms, the more solute you add to the liquid, the higher up the boiling point goes and the lower down the freezing point goes. Okay? Ha! So a solution has a lower freezing point than the freezing point of the pure solvent. That's actually correct. I don't know what happened with the other two. Indeed. So, these are the answers to those questions, to those problems that we did together. So if you go through this at home or you go through the PowerPoint alone, not this video, then if you work on the questions and you want to test yourself and see how you did, here are the answers for you. Okay? So you can check your own work. Now, sometimes, or I should say, you have to be careful when using this formula if they give you the volume in milliliters and not liters. So let me show you what I mean. This question says, what's the concentration of a solution containing 2 moles of sodium hydroxide in 500 milliliters of solution? Now you're going to say to yourself, oh, concentration, and they gave me moles and liters. So, terrific, I'll use the molarity formula. And you will. You're totally right. But notice the volume was given to you in milliliters, but the formula asks you for liters, right? The volume they gave you was milliliters, but the formula asks you for liters. So you're going to have to convert milliliters to liters. And you do that by dividing by 1,000. So once you convert it, you now have 0.5 liters, and there you go. You can get your answer. Okay? There's one of these types of questions on the exit ticket. I think it's the last question. It's called a challenge question. So do your best with that. Okay? Just remember, in order to use this formula, the volume has to be in liters. If it's in anything other than liters, you have to convert it to liters. Okay? And more often than not, they do this liter milliliter thing. Just an FYI. Okie doke. I know that was a lot to take, and I'm sorry. But we're at the end. So make sure you do the exit ticket. Okay? It's a 10-question exit ticket this time on the Google form. Alright? And if you have questions, email me. Or you can ask me during our regularly scheduled class periods. Okay? Have a great day, guys. Be well.